Hello, everybody. We're going to continue our discussion on thermal radiation. We know what temperature is now. We know that as objects get hotter, they give off more and more light. They become brighter. They also will go from, say, giving off longer infrared wavelengths mostly to transitioning over to giving off visible wavelengths. And you can bet that as we heat it up, if you get it hot enough, it gives off visible wavelengths, and it's still going to give off visible, and eventually it'll give off things like ultraviolet wavelengths. I've already talked to you about that dense objects will emit light according to their temperatures. Every dense object in the universe has a temperature, so everything in the universe is emitting this, every dense object in the universe is emitting this thermal radiation. And we're after coming up with a way where we can determine the temperature of things in the universe and to have an innate understanding of the connection between heat or temperature and light. Let's go ahead and dive right in, and we are going to introduce a hypothetical, a imaginary, it doesn't really exist in nature, construct, a perfect object. But if we're going to talk about a perfect object, we have to say perfect how. So what I'm going to talk about is what is known as a blackbody. None of these exist in nature. Some things are really darn close to it, and every dense object in the universe, like you and I, this juggling ball, the planet Earth, stars in the sky, the sun, our local star, are very close to behaving like a black body. And since it's ideal, all we have to worry about is the how of everything, the physics of it. So let's discuss what this idealized object called a black body is. So a black body, represented here by a perfectly black object. You can picture a perfectly black sphere if you wanted to, so you can get some of that really fancy paint that you keep seeing on the internet that makes things that say it's the blackest black that's out there. Imagine this ball coated with that, and you're really darn close to a black body at that point. But what makes it a black body? Well, a black body will absorb all incoming light, so all light, doesn't matter what the wavelength or the frequency is, all light that hits it is absorbed by it. No light is reflected, so zero reflectance. So you couldn't even really see this object because there's no light reflecting off of it to come to your eyes. All things in nature reflect at least a little bit of light, so these don't really exist. But a black body would absorb all light of all wavelengths perfectly. That means reflect none of it. That means all the energy of that light is just getting dumped into that black body. And that black body, in response, all the little particles that make up that black body are going to start moving around a little bit faster because they got a whole bunch of energy. And now we know that particles moving faster means higher temperature. But the black body is not just going to sit there and absorb. The black body can also emit that energy back out into the universe. And it'll do so according only to the object's temperature. So a black body, it will absorb all light that falls on it. And then what it's going to do is that will set it to a certain temperature. It'll get all those things wiggling around, all those particles wiggling around in it. And then it will re-radiate all of that energy that it's absorbing back out into the universe. And it'll do so according only to its temperature. It'll emit what we call thermal radiation or black body radiation. So what is black body radiation? Well, it's going to emit over a very distinct range of wavelengths with a very distinct pattern. It'll be a very large range of wavelengths that will extend through several parts of the electromagnetic spectrum. And if you look at each wavelength will have a very distinct brightness associated with it. It'll be giving off a certain brightness of that color of light. So the total amount of energy that is re-emitted is the same amount that it was originally absorbed, but it's now going to spread out all of that energy over a range of wavelengths with a very distinct pattern. And it's that distinct pattern that we're going to take advantage of. This re-emitted light, this perfect idealized scenario, so a black body would perfectly re-emit the light according to this distinct pattern. And we call that black body radiation, which is really what we'd also call thermal radiation. So why do we call it thermal radiation? Because how it's going to emit that energy back out into the universe, that light back out into the universe, is determined by one property, temperature. All right, so let's take a look at this distinct pattern. Here we have our black body sitting over here. It's going to be absorbing energy as it goes into it. And then, according to its temperature, it's going to re-radiate that energy out, spread out over a range of wavelengths. So on the x-axis here, I'm going to spread that light out over in a range of wavelengths. On this one, it's only going from pretty much 0, so gamma rays, all the way through our x-rays, and from x-rays to ultraviolet to our visible light, then to our infrared light, and out to 2 microns, that's still infrared light. But it'd keep going off this way as well. And notice that this is tracking the wavelengths here. And then this, the y-axis, you can think of the y-axis as technically flux. We'll get there. But for now, just think of the y-axis as brightness. How bright is each one of those wavelengths? If you're thinking about that in the visible spectrum, how bright is the violet light? How bright is the blue light? How bright is the green light? How bright is the red light? And though they won't all be exactly the same, in this case, they're mostly about the same, but it's giving off the most green light. So it's brighter in green light than it is in red light, because if we go to the red part, it's at a lower brightness value. Green part's at the highest, and then violet is even lower. And over here, infrareds are even lower. All right, so we call this distinct pattern thermal radiation. It also goes by the names of a blackbody spectrum, because it is a spectrum, light spread out over the wavelengths. So it is a spectrum emitted by a blackbody. And since it's got a nice distinct curve shape, a lot of people just call these blackbody curves as well. What's going to determine the shape of this curve is going to be the temperature. This is what we call our thermal radiation. But I want to talk a little bit about what I mean by this distinct shape of it. We're going to break that down into 2 different components. What we're going to be looking at you can see that if we're tracking this as we move along wavelength and tracking how bright each wavelength is, we have this nice rise up where each wavelength, as we move towards the longer wavelengths, is getting brighter, 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 reaches a peak. And then it gets dimmer, 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 dimmer. So whenever we talk about the shape of it, one of the things we want to know and ask ourselves, by shape, I'll define part of the shape as, where is this peak? What wavelength does this peak lie at? A peak wavelength. The other part of the shape that we're going to talk about is, how big is this curve? Is there a really small one? So is there a little bit of area underneath the curve? Is there only a little bit of light being given off? Is it not very bright? Or is the curve really, 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 really big? Or is it giving off lots and lots and lots of light? There's a lot of area under this curve. The object is giving off a lot of light. It's very, very, very bright. Okay, now I know this is really weird and different to look at. So what I want to do is I want to show you a simulation of an object heating up, and we'll not only see it heat up like we watched the eye of my stove heat up and turn orange hot, but we will also look at its blackbody spectrum, the light that it gives off according to its temperature as that temperature changes. Let me go ahead and bring up that simulation for us to take a look at. And I'm going to talk our way through it. All right. For this one, I really like to zoom in a little bit. Okay, so here we have our wavelengths again. And notice that this one is focused on the visible spectrum, and it even color codes it for us. So we have the blue, and then we have the green, and then we have the reds. Over here, we're going to have this nail, and they're just going to run a current through it, which is going to cause it to get really, 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 really hot. And it'll tell what the temperature of the nail is here. And here it's going to show us a blackbody curve through the visible part of the spectrum. And up in this little inset right here, it's going to show us, notice it goes from not just from 300 nanometers to 800 nanometers, 0.3 microns to 0.8 microns. This one goes all the way from 0 to 10 microns. So we can see the full shape of the blackbody curve. Now, as it heats up, pay attention to how big the curve is and where that peak is. I'm going to go ahead and hit start. You can see starting to glow red hot. Here's our blackbody curve. It's getting larger. And notice that, oh wow, it's giving off lots of red light. And now it's giving off red light, orange light, mixing in some yellow light and all the other colors, but a whole lot of red is glowing yellow hot. Now it's going to break. So we saw that it got bigger, and then it started to give off visible wavelengths as well, shorter wavelength radiation and more shorter wavelength radiation, more short wavelengths of light. All right, so I'm going to go ahead and go through this really quickly again, and this time I want you to watch what happens to this peak and ask yourself, is it moving to longer wavelengths or is it going to be moving to shorter wavelengths? And just observe. So as this gets hotter, what direction is it moving? It's moving towards shorter wavelengths. That peak moves to shorter wavelengths as the temperature increases. Notice now, as the nail hit about 1800 Kelvin, it got so hot that it broke. So now that there's no current running through it, the nail's just going to cool down. So the first part of the video, we watched the nail heat up and the blackbody curve get bigger and the peak move to shorter wavelengths. I'm going to predict that as it gets cooler, it's going to do the opposite. That the curve is going to get smaller and this peak is going to move to longer wavelengths. Let's see if my hypothesis is right. Cooling down, giving off less visible light, not really giving off much blue light anymore, not really giving off any yellow light, glowing red hot. Oh, this peak is moving to longer wavelengths and the curve is getting smaller. So there is a nice little simulation of how a blackbody curve changes with temperature. One other thing is notice that it has a unique shape for every temperature. We can define, given a temperature, there will be a unique blackbody curve associated with that temperature. And notice here, this entire time, I've been assuming that this nail is a blackbody. It's really darn close to a blackbody. Not quite perfectly like a blackbody, but pretty much indistinguishable in the way that it gives off light. Okay, so let's go ahead and head back. Actually, no, let's go ahead and head to another simulation. So this is going to be one of the University of Nebraska-Lincoln simulations. The ones that I've put several links to, and I'll put a link in the README, the week 6 README for this one, so you can play around with it. And this is a blackbody simulator. So here is where you can create your own blackbody curves. And you can look at how or where the peak position is and how that changes with temperature, and how big the curve is and how that changes with temperature. Notice that we are going to be looking at how blackbodies, or how things that approximate blackbodies, emit light. And the only control we have on this is the temperature. So the shape of this blackbody curve, the type of thermal radiation, the characteristics of the thermal radiation are only determined by the temperature. So right now the temperature is set at 7,500 Kelvin. I'm going to give us some indicators to help us out here. I would like to know how bright this object would be. So how bright would it be? Well, it's giving off this much of this wavelength, this much light at this wavelength, this much light at this wavelength, a whole lot of violet light. What if I just added up all the light that it's giving off? That would look something like this. So that would represent, this represents the total brightness. And I would like to track where that peak is, since that seems to be important. So I can turn on the indicate peak wavelength, and for a blackbody that has a temperature of 7,500 Kelvin, it would have a peak wavelength of 386.4 nanometers. Almost as if there's some way to calculate that there is some physical law that allow us to determine that peak wavelength. Now, what I'll do is I'm going to lower the temperature. As I lower the temperature, this peak is going to move to longer wavelengths, and the curve should get smaller. So I'm down to, let's go to about 5,800. This is about the surface temperature of the sun. So the sun as a black body gives off thermal radiation that looks like this. Notice that it has a peak at about 500 nanometers, right about where green is. So the sun gives off mostly green light, but not a whole lot more green light than purple light or blue light or red light. And if you mix all the colors of light relatively equally, you get white. If you go to outer space and look at the sun would look white. It looks yellow due to our atmosphere when we view it from here on Earth. It has a peak wavelength of about 500 nanometers. So notice that the curve got a lot smaller. It actually has a value for that over here. And the peak wavelength is now at a longer wavelength. I could keep getting colder and colder and colder, and the curve just gets smaller and smaller and smaller, and that peak just keeps moving to longer and longer wavelengths, still in the visible. But if I make it cold enough, so down to about 3,400 Kelvin, notice that the peak is now in the infrared part of the spectrum. And yes, it's giving off some red light, but it's giving off more infrared light. This object would be glowing red hot. All right, so I've been locking the scale. That way we can see the peak, we can see it grow. So what I want to do is I'm going to go ahead and auto scale. So notice now the curve is going to remain. It's going to look like it's the same size, but the numbers are going to get a little bit bigger. What we want to do is I'm just going to I'm going to lock the scale so it's larger. Okay, so now we can go back to our 7500. I know it looks different, but it's the exact same curve. The numbers on the y-axis, how bright it is over here has just changed. If you were to go back, you'd notice that the number that it reads off, so if I were to go over here and see where this is on the y-axis, exactly the same numbers. I just wanted to rescale it so we can see what happens as I increase the temperature past 7,500. The peak should move to shorter wavelengths, so notice it's right here on the very edge of visible light in the violet part of the spectrum. The peak should move into the ultraviolet. Hotter things like giving off shorter wavelength radiation. And that's indeed what we see, and we see the curve is getting bigger and bigger and bigger. So by the time I reach a temperature, kind of like the surface temperature of a star called Vega, or something like that, you have a peak in the ultraviolet at about 250 nanometers, very short wavelength. And the curve is much, 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 much bigger now, so that star would be intrinsically brighter. So what have we observed? As the temperature goes down, this peak wavelength moves to longer wavelengths, and the curve gets smaller. As we go to higher temperatures, the peak wavelength moves to shorter wavelengths, and the curve gets bigger. Almost as if there's going to be a rhyme and a reason to that. Almost as if there will be some laws that govern this thermal radiation. Almost like Dr. Lindsay is going to make his next video on the thermal radiation laws. And this is just a summary slide just to really go ahead and reinforce. I wanted to show you with a simulation. This is just showing, here's a blackbody curve. So remember, every temperature, as we just saw, has a unique blackbody curve. And as we increase the temperature, the curve gets bigger, which is the same as the object gets brighter. It's emitting more light, and it preferentially starts emitting shorter and shorter and shorter wavelengths. We can track that by following where the peak is. At 3,000 Kelvin, the peak would be here in the infrared. At 4,000, it would be here in the infrared. A blackbody that has a temperature of 5,000 has its peak of the blackbody spectrum. The color it likes to give off the most of is red light. That's the brightest color that it's emitting. It's emitting a lot of different colors, but it's emitting the most of this wavelength of red. And then as you heat up to 6,000, your peak is here in the green. And this would be the blackbody spectrum, the blackbody curve, the thermal radiation that our sun gives off. All right, so I'll put a link to that UNL blackbody curve simulator and the little simulation on the README for this week. And next video, we will actually talk about the thermal radiation laws, the rhyme and the reason, the how, the physics of it all.